Hello all and welcome to Physics with Pranav. If you're new here, I'm Pranav, a former CAIE science and math student, a tutor for GCSE and A-level students from around the world, and an IGCSE world topper in science from back in 2013. If you're a GCSE student preparing for your physics exam, I can imagine that there are two things that are top of your mind. The first is, what are the most commonly tested topics, or what are the topics that I need to focus on so that my preparation is as effective as can be? And the second question is, right, how do I apply these concepts to past paper questions? Which is why I want to introduce in my videos a simple three-step approach which I used and that I taught to my tutees from around the world, which helped all of us achieve excellent grades. And I hope that by applying this approach, you will ace your exams as well. So it's a three-step process. The first is to go and look at recent past paper questions and try and understand for each chapter what the most commonly tested concepts are. Now, yes, the general wisdom is to prepare the entire curriculum and be confident in the entire curriculum, because you never know when a surprise question is going to show up that hasn't been tested ever before or hasn't been tested in years. But I think as a general rule of thumb, if you want to prioritize your preparation, it's always a good idea to look at recent past papers and try and understand the patterns and the most commonly tested questions from these past papers. So that's the first thing we're going to do in the three-step approach. The second thing is, once you identify the key concepts, it's important to be able to solidify your foundations in these concepts. So am I really clear with what I will likely be tested on? Am I clear with the concepts? Am I clear with the formulae, the calculations? It's essentially just making sure that you solidify the foundations. And the third step is to be able to apply these concepts to actual questions from past papers, right? So this is the three-step process that we'll be applying. The way I've structured my videos is I tend to make two sets of videos. The first set of videos, of which this is an example, is where I actually show data from recent past papers on the most commonly tested concepts, and then we dive a little bit deeper into these concepts so you solidify your understanding of them. And in the next set of videos, for the same chapter, I will then be applying these commonly tested concepts in past paper questions, so you understand the approach and methodology that I use, and you also feel confident on how to approach these types of questions in past papers. So this is essentially going to be my approach. So in this particular video, we will be looking at chapter 4, turning effects of forces from the CAIE curriculum. I just want to let you know here as well that if you are not a CAIE student but are a GCSE student from another curriculum, don't worry about it. Like, although the exact chapters might be different, the content that's covered in these videos and the methodology that is applied when solving past paper questions will definitely prove helpful to you, irrespective of what board you study in, right? So without further ado, let's take a look at chapter 4, turning effects of forces. So using my three-step approach, the first step is to look at the most commonly tested concepts for this chapter from recent past papers. So I've taken 2020 to 2022, and I've looked at both paper 2 and paper 4, paper 2 being the multiple choice paper, paper 4 being a theory paper. I've looked at all three variants for both papers, and I've looked at questions from Feb, March, as well as summer, which is May, June, and the winter editions of these exams, winter being October, November. And obviously the general advice is to be prepared with the entire curriculum, so you are confident with the concepts that are tested, and you will be prepared for surprises if they do arise. But if you were to be effective with your prep, and if you want to streamline it, then it's always a good idea to look at the most recent past papers and to try and identify the concepts that are tested, because there's a very good chance that they probably will be tested again. So in this particular chapter, unsurprisingly, the most commonly tested concept is calculations based on moments and equilibrium, turning equilibrium. So this concept was tested in 13 of 21 past papers for paper 2, and in 4 of 21 past papers for paper 4. So again, easily the most tested concept. You also have questions arising from time to time around describing the turning effects of objects using moments, and questions around the center of mass, identifying the center of mass, identifying how any changes to the structure of the object can affect its center of mass. You will find questions on this, but questions around these two are more rare than questions around the calculations. You can also see that I've highlighted the paper 2 box in it's got a bold border, and the reason for that is this concept, or this topic rather, of turning effects of forces is most commonly tested in paper 2. You will find the rare paper 4 question, but you are almost guaranteed to find a paper 2 question from this particular topic. So I know that most of you write your paper 2 exams and your paper 4 exams separately. They might be on the same day, they might be on different days, but the thing is, if you are preparing for your paper 2, I would definitely focus on this concept and this topic. But if you're looking at paper 4, then, if you had to prioritize other topics and concepts, I would prioritize them over this particular chapter, because you don't find that many questions from this chapter in paper 4. So then we'll be looking at the moment and equilibrium calculations, and how we could do them well. So firstly, we'll be looking at what moments are. So essentially, the moment is the turning effect of a force. The clue is in the name of the chapter. And to look at the turning effects of forces, let's have a quick look at the system and try and understand it. So we've got two objects. We've got A and B. A has a mass of ma. So this is just a common notation where the notation for mass is m, and because it pertains to A, we call it ma. And for B, it will be mb. And then essentially they are sat atop a rod, and the rod is balanced by this conical object here. We'll get to that in a second. And essentially the conical object is right at the center of the rod. And the distance of A from the center is dA. The distance for B is dB. And if you think about the force that A and B exert, we're not applying any additional forces to A and B. So the force that they exert on the rod is the weight of each of these objects. So the weight of A is the mass of A multiplied by the gravitational acceleration near the surface of the Earth, and the same for B is the mass of B multiplied by its gravitational acceleration near the surface of the Earth. And I've essentially denoted the weight of A as WA, the weight of B as WB, and the weight here is essentially the force that these objects are exerting on the rod. And now we come to the weight of the rod itself. The weight of the rod acts at the center of the rod. So it has a weight of W rod, which is also equal to the mass of the rod multiplied by the gravitational acceleration. Now the key thing to understand is the weight acts on the mass of the object, right? So if you have a symmetrical object, i.e., there is no, the object is the same in any direction that you orientate it in, and its mass is evenly distributed within its volume. So we can assume that, there is no extra mass on the top right of A or on the top left of B, but rather the mass of B is distributed evenly throughout B, the mass of A is evenly distributed throughout A, the mass of the rod is evenly distributed throughout the rod. The weight still appears to act at a certain point within the object. Although gravity is equally pulling on all the regions of mass within an object, the weight appears to act from a certain point. It appears to originate from a certain point, and that point is referred to as the center of mass. So the center of mass for A will be at the center of A, the geometrical center of A. The center of mass for B will be at the geometrical center of B. And the center of mass of the rod will be at the geometrical center of the rod, which is right at the center, which is where the rod is perched on top of this object, right? So center of mass is a concept that's not really tested often in your paper, so we're not going to explore the concept of center of mass in a lot of detail in this particular video, but I will be showing how you will be tested on that concept in past papers, by walking through a question where they did test about, identifying the center of mass and how it changes when the structure of the object changes. But for the time being, if you have a geometrically symmetrical object and if its mass is evenly distributed within it, then you can assume that its weight acts from the geometrical center of the object, which, as I've said, for A will be the center point of A, for B will be the center point of B, and for this rod, it will be the geometrical center of the rod. Right, okay. So what is this object and what is it trying to do? So we know that it's balancing the rod, on top of it. But essentially at this particular point, there is no turning effect. Yeah. So you can think of this as a seesaw, right? You can think of this seesaw, and you can think of object A and B as, say, two people sat on a seesaw, and that's the middle of the seesaw, right? So at that point, there is no turning effect. But on the two different sides of the seesaw can turn, right? It can go down this way, it can go down that way, it can go up that way, it can go up that way. So essentially, obviously with the seesaw, it's going to hit the ground. It's not going to like turn the entire way around, but it can go up and down, around that point. But it doesn't go up and down at that point itself. That particular point stays roughly the same. Yes, it may turn a little bit like that, turn a little bit like that, but there is no actual turning effect at the center of that point. The turning effects happen at any distance from that point in the center. However small that distance is, there will be a bit of a turn. It may go up or down a bit, up or down a bit, or it could be there, up or down a bit, up or down a bit. But at that particular point of the center, there is no turning effect. So that particular point in the center is called the pivot. And usually that object that balances the rod or the bar or whatever it is, on which other objects that can create turning effects are placed, is that object that balances it is usually called the pivot. So here, this triangle is the pivot. That center point there is the pivot. And the key thing to take away, there is no turning effect at the pivot, but there is turning effects around the pivot. That's the key thing to take away. So the force that object A exerts on this rod, which is essentially its weight, will make the rod turn in an anti-clockwise direction. Yeah, so if you think of the 12 o'clock as the top and the 6 o'clock as the bottom, it makes you go from 12 to 6, like that. Usually, the clockwise motion that we used to in clocks will be from 6 to 12, so that's the clockwise direction, but it makes the rod essentially go from the 12 to 6 direction. Whereas B, again, the force that B exerts is due to its weight, and that makes the rod go from from the 12 to 6, or rather the 6 to 12 direction, 12 to 6 this way, or 6 to 12 that way direction. So that's the clockwise direction, right? So you've got an anti-clockwise turning effect caused by A, and you have a clockwise turning effect caused by B, right? And the reason these objects can cause turning effects is because they're not placed at the pivot. They're placed a certain distance away from the pivot, okay? And that distance is given as dA for object A and as dB for object B, right? So how do you calculate the exact turning effect, or the exact moment? The turning effect is equal to the moment. How do we calculate that value? So that value is essentially the force exerted perpendicular to the pivot at a certain distance from the pivot. So if I break down what I just said, and I took the example of A, you've got a force exerted by A, so you've got a force, Fa, or Wa, and that force needs to act perpendicular to the pivot. So you can see that, that's the pivot, that's the rod on it, and it acts perpendicular. Is a 90-degree angle there, and it acts 90 degrees to the point of the pivot. The point of the pivot is there. And it has to act a certain distance from the pivot, because if it's, not acting at a distance from the pivot, i.e. it's on the pivot, then there is no turning effect. So it has to act a certain distance, which is dA. So the product of the force acting perpendicular to the pivot at a certain distance from the pivot is basically equal to the moment of, that particular force. So moment of A, or the moment caused by the force exerted by A, to be more accurate, is the product of the force that A exerts, which is Fa, multiplied by the distance that this force acts from the pivot, dA. So it's Fa multiplied by dA. The same for B will be Fb multiplied by dB. And then if you had the moment of the rod, because, well, the rod also exerts a force downwards, which is the weight of the rod, that would be F rod d rod. But then you notice that the center of mass of the rod is right above the pivot, or right at the point of the pivot. And essentially there is no, although the force of the rod acts perpendicular to the pivot, there is no distance from the pivot for this force. So if there's no distance, then d rod would be 0. Then F rod multiplied by d rod, or F rod multiplied by 0, is 0. So there is no turning effect caused by the weight of the rod. So hope that explains the concept of moments. If we look at another example where the pivot is not at the center here and it is at one of the ends, again that helps us. We will look at trying to understand the concept of equilibrium by looking at a scenario there. So in this system, we've got a pivot here, which means there is no turning effect there. And then we've got essentially the weight of the rod acting at the center of the rod. Yeah. And that's going to be F rod, which is equal to W rod, which is going to be the mass of the rod multiplied by the gravitational acceleration. And then you've got you have just object A here, which is acting. So the F rod is acting at a distance of D rod from the pivot. And then you've got object A, which has mass A, which has a weight of WA or a force of FA, as acting from a distance of DA. And I think from the previous example, we know that the moment of A would be will be FADA, sorry. The moment of the rod, or the moment due to the weight of the rod, will be F rod D rod, or W rod D rod, however you want to say that. And then you have a force FB. And FB is actually, so we can see that the force due to A, which is FA, and the force due to the rod, F rod, are both acting downwards, and they're both causing an anti-clockwise moment. So it's making you go from sort of 12 to 6. So it's making you go like that. This F rod is also making you go in an anti-clockwise direction. So they're both making the rod turn in an anti-clockwise direction. If there were no force FB, which makes the rods, which acts in a clockwise direction, and counters the anti-clockwise moments of these two forces, FA and F rod, then the rod would just sort of, it would just go down like that, in the anti-clockwise direction. So you could think of it a bit like, if that was a seesaw and there's no one sat towards the right of the seesaw, and there's only someone sat towards the left, the right side of the seesaw, the seat goes all the way up, and the seat where the person is sat on the left goes all the way down. Yep, so it's an anti-clockwise moment. But in this scenario, we've got a clockwise force. The clockwise force doesn't act towards the right. All of the forces in this scenario act towards the left of the pivot. And this force acts upwards. So, you have to be used to this scenario as well, right? So this force acts upwards. It acts a distance dB. We call that force B. And then, it acts a distance dB from the pivot, so it'll have a moment of FB dB. So we've got essentially here three moments. The moment due to the weight of the rod acting at the center of mass of the rod, which is here. It has a value of F rod, and it acts a distance D rod from the pivot, so it has a moment of F rod D rod. And then we've got the moment caused by object A, and that is due to the force exerted by object A, which is FA, or the weight of the object, which is WA. It acts at distance dA from the pivot, so it has a moment of FADA. And we know that both FADA and F rod D rod are anti-clockwise moments because they try to pull the rod down from the 12 o'clock to the 6 o'clock in this direction, not from the 6 to the 12 o'clock. And you've got the third force, which is FB. FB acts at a distance dB from the pivot, which means the moment of FB will be FB dB, and it acts in the clockwise direction, essentially making the rod move from the 6 o'clock to the 12 o'clock. So those are the three forces that are acting. You've got one clockwise force, and you've got two anti-clockwise, you've got one clockwise moment, you've got two anti-clockwise moments. And at equilibrium, so essentially I'm trying to illustrate the concept of equilibrium here. The total clockwise moment, that is the moment here that is exerted by force F, which is also FB dB, must equal the total anti-clockwise moment, which is the moment exerted by object A and the rod, which is FADA and F rod D rod. So at equilibrium, the total clockwise moment, which is FB dB, has to be equal to the total anti-clockwise moment, which is FADA plus F rod D rod. So you will find questions where you will be told that the system is in equilibrium, and you need to be able to calculate, you might be missing either a force, or you might know the value of a force, but you might be missing a distance, and you have to be able to equate, using this formula here, that the total clockwise moment is equal to the total anti-clockwise moment. You'll be expected to calculate the missing quantity, right? So the cue that you need to look for is the fact that the system is in equilibrium. So this is, again, a very commonly tested concept. So in your past papers, you will be asked questions around just being able to calculate moments. There's an object that is sat or that is placed a certain distance away from the pivot. What is its moment? That is a very straightforward question. You'll be asked to calculate that. You'll be asked to use the concept of equilibrium to be able to calculate a missing force or a missing distance. The important thing to remember is that the pivot doesn't always have to be at the center of mass. We saw in the previous slide that the center of mass and the pivot point aligned, but this doesn't have to be the case. So watch out. A common clue, is usually when the pivot is a certain, if it's not at the center of the rod or the object, but if it is at one of the ends, then you can expect that there will be a center of mass that is acting as well, that is causing a moment. Obviously, well, if it's acting to the left of the pivot, it'll usually cause an anti-clockwise moment. Whereas on the other hand, if say the pivot was here on this end towards the left, and all the forces acted towards the right, then it would have a clockwise moment. So again, these are just things to keep in mind. And you would also have scenarios, again, if you see my video on the solved past paper questions for chapter 3, which is forces in motion, you will be able to find scenarios where you have to describe if an object is in equilibrium. So you would have an object on which forces act on it. So not only should the net forces acting on it balance, but there should also be no turning effects. So those are the other types of questions that you commonly get in this topic. But these are the key concepts that you need to be aware of. If you are clear with these concepts, you should be able to solve most of the calculation questions in the past papers, which are, again, the most commonly tested questions in your past papers. I will be releasing a video where I will take you through, paper 2 questions and paper 4 questions. I will also be looking there at scenarios where you will have to describe moments and scenarios around moments in equilibrium, and scenarios around the turning effects caused by forces. And we will also look at a question that has shown up in recent papers around center of mass, describing center of mass, and describing how, when you change certain things about the object or the structure of the object, you can influence the center of mass of the object. So I haven't covered it in this video because it was only tested in one paper from 21 that I looked at. But I will still be showing you how, if such a question shows up, you will have to answer it. Anyways, I hope you found this video helpful. If you did, please subscribe to my channel. Please like this video and share this video with others who you think will benefit from viewing this content as well. And I look forward to seeing you in my next video, where I show you how to apply this concept to past paper questions. Thank you very much.